Hi, my name is Ayush Malpani and today I am going to tell you about four topics that is Hermite polynomial, Laguerre polynomial, moment of inertia matrix and going to explain you about rocket propulsion using Hamiltonian mechanics and Lagrangian mechanics. So firstly I am going to start with Hermite polynomial. Firstly, what is Hermite polynomial? Hermite polynomial are nothing but set of orthogonal polynomials over domain minus infinity to infinity with weighing function e to power minus x square. Hermite polynomials are set of orthogonal polynomials over domain minus infinity to infinity with weighing function e to power minus x square. This is the definition of Hermite polynomial. There are basically two ways of standardizing Hermite polynomial. One is probabilist Hermite polynomial, which equals x minus d upon dx to the power n into 1. And another one is physicist Hermite polynomial, which equals 2x minus d upon dx to the power n into 1. There's only a difference of 2 in probabilist Hermite polynomial and physicist Hermite polynomial. Now I am going to tell you about the first few Hermite polynomials, that is h0x equals 1, h1x equals 2x, h2x equals 4x square minus 2, h3x equals 8x cube minus 12x, and h4x equals 16x to the power 4 minus 48x to the power 2 plus 12. These are the first few Hermite polynomials. Orthogonal property. Polynomials, Hermite polynomials are orthogonal with respect to the weight function. That is, are orthogonal with respect to weight function, where weight function, that is wx, equals e to power minus x square or e to power minus x square by 2. By orthogonality, I mean minus hmx, hnx, wx equals 0, where m is not equal to n. That is, integration of hmx and hnx and multiplication of with wx from minus infinity to infinity equals 0, where m is not equal to n. Now, another property of Hermite polynomial is its differential equation. That is, Hermite polynomial are nothing but the solution of the differential equation e to power minus x square by 2 Hermite polynomial are nothing but the solution of this differential equation. It is the another property of Hermite polynomial. Now, the third property of Hermite polynomial is its recursive property, which is very important. Recursion relation of Hermite polynomial. Hermite polynomial satisfy this recursion h in nx minus, where h in x stands for probabilist Hermite polynomial. So probabilist Hermite polynomial satisfies this uh, recursion relation. This is the third property of Hermite polynomial. Now I will tell you about the expected value of Hermite polynomial. Expected values. If we treat Hermite polynomial to be a random variable with normal distribution and standard deviation 1 and expected value mu, then that is, if x a random variable with normal distribution, that is with standard deviation equals 1 and uh, expected value mu, then expected value of probabilist Hermite polynomial equals u to the power n for probabilist Hermite polynomial. This is the fourth property of Hermite polynomials. This is all I have to tell you about Hermite polynomials. Now I will tell you about another type of polynomials, that is Laguerre polynomials. So what are Laguerre polynomials? Laguerre polynomials are solution to the differential equation xy double dash plus 1 minus x y dash plus ny equals 0 with initial condition y equals 0. As you can see, this is a 2-degree differential equation. So how Laguerre polynomials look like? Polynomials are given by ln x equals summation k from 0 to n minus 1 to the power k upon k factorial and ck x to the power k. This is how Laguerre polynomials look like. Now I will tell you about the contour integral representation of Laguerre polynomials. Integral representation. Equals 1 upon 2 pi iota e to the power minus tz upon 1 minus t t to the power n plus 1 dt. This is how the contour integral representation of Laguerre polynomials look like. As we have seen the recursion relation in Hermite polynomials, there also exists a recursive relation in Laguerre polynomials. So recursive relation for Laguerre polynomials look like n plus 1 ln n plus 1 n plus 1 minus x ln x minus n ln minus 1 x. There is also another form of recursive relation for Laguerre polynomials, which looks like x ln dash x equals n ln x minus n ln minus 1 x. These are the two recursive relations which Laguerre polynomials satisfy. Now I will tell you about the first few Laguerre polynomials, as I have told about first few Hermite polynomials. Ln 0x equals 1. Likewise in Hermite polynomial, ln1x equals 1 minus x, ln2x equals x square minus 4x plus 2 whole divided by 2, ln3x equals 1. This is all I have to tell you about Lagrange polynomials. Now I'm going to tell you about moment of inertia matrix. Firstly, what is moment of inertia? Moment of inertia is nothing but a tensor quantity that determines torque needed for desired angular acceleration. Uh, Moment of inertia also depends on the body's mass distribution and axis chosen about which we desire to rotate the body about. And for bodies constrained to move in a plane, it is sufficient to consider its moment of inertia just by axis perpendicular to the plane. But for bodies free to rotate in 3D, we have to describe its moment of inertia by a 3 by 3 matrix. That is, for bodies constrained to move in plane, constrained to rotate in plane, moment of inertia can be represented by just an axis perpendicular to plane. But in 3D, we have to represent its moment of inertia by a 3 by 3 matrix. 3 matrix where each expresses Lx, Ly, Lz. That is a moment of inertia with respect to x-axis, y-axis and z-axis, and likewise for 3 by 3 matrix. Now I will tell you about the inertia matrix for a rigid body. Inertia matrix for rigid body. Just consider a system whose center of mass with respect to the origin is at a relative position r. It's from center of mass any particle, ith particle is at a position delta r I, and ith particle with respect to the origin is at position ri vector. So delta ri vector equals ri vector minus r vector and vi vector, that is velocity vector of the ith particle, equals omega cross ri vector plus vr vector. This is absolute velocity of the ith particle, and this is the relative position of the ith particle with respect to center of mass. Okay, and consider this rigid body to be the collection of n particles. Pi is equals to I from 1 to n. That is a rigid body of collection of n particles from 1 to n. Then its angular moment, where IC equals minus summation I from 1 to n mi delta Ri square, where delta Ri is position of ith particle with respect to center of mass, and IC, that is moment of inertia matrix, is symmetric matrix with respect to center of mass C. Now I will tell you about how kinetic energy of a rigid body and torque of a rigid body can be written in terms of the inertia matrix. Firstly, kinetic energy K equals 1/2 omega IC का plus half mvc square, where IC is nothing but uh, inertia matrix. And torque of a rigid body can be written as AC alpha plus omega cross IC omega, where alpha equals angular acceleration, IC equals inertia matrix, and omega equals angular velocity. This is all I have to tell you about moment of inertia matrix. Now I will try to explain you rocket propulsion using Lagrange's and Hamilton's mechanics. So for, firstly I will try to write kinetic energy of rocket, that is half mv square, where v can be written as dq by dt, which is same as q dot. So half m q dot square. This is the kinetic energy of rocket, where m is the mass at that instant, at particular instant. Potential energy equals mg, m into g into q. So Lagrange's and can be written as L equals kinetic energy minus potential energy, which equals half mq dot square minus mgq. Now from the Lagrangian equation we know d by dt equals. Now from Lagrangian equation we know differentiation of dl by dq dot with respect to time equals dl by dq. So dl by dq dot equals mq dot and dl by dq equals minus mg. Therefore d by dt of mq dot plus mg equals 0, and mq dot double dot plus dm by dt of q dot equals minus mg. This is the Lagrangian equation we have got from Lagrange's equation. Now following the same approach but using Hamilton's approach. For Hamilton's mechanics we know H equals kinetic energy plus potential energy, that is equals half mg q dot square plus mgq. For Hamilton's equation, dp by dt equals minus gh by dq, p equals mq dot. So Hamilton equal substituting this in above in equation number 1, so Hamilton equation becomes d by dt mq dot minus gh by dq equals minus mg. So mq double dot plus dm by dt of q dot equals minus mg. This is the equation we have got from Hamilton's mechanics. As we can see, the equation we got from the Lagrangian mechanics and Hamilton mechanics are same. So this is the final result.